Welcome to ilectureonline, and here we're going to use Gauss's law and a Gaussian surface to find the electric field inside a spherical object that has charge throughout the entire object. And here we're going to find the electric field strength outside that very same object. So here what's different is that we don't have a conductor with charge on the surface. Here we have an object with surface all throughout the sphere. So these are spherical shaped objects with charge equally distributed everywhere inside the sphere. And we want to know the electric field strength, let's say 20 centimeters away from the center, but still inside the sphere because the sphere has a radius of 30 centimeters. The total charge in the sphere is 2 times 10 to the minus 6 coulombs. So what's the electric field strength at this location right there? So what we do here is we draw a Gaussian surface where the edge of the surface is right at the point where we want to know the electric field strength. Realizing that the electric field will always be perpendicular away from that Gaussian surface pointing outward and will be exactly the same strength everywhere along that surface. That's why we can use Gauss's law like this. So since the electric field will be perpendicular to the Gaussian surface, this part of the equation simply becomes the strength of the electric field times the area, the total surface area of the Gaussian surface, so let's call that A, and that equals the charge inside divided by epsilon sub naught. So how much charge is now inside the Gaussian surface? Well, we were given the charge inside the whole sphere, so we have to find the ratio of how much is inside the Gaussian surface compared to inside the whole sphere, and that simply will be the ratio of the volume of the Gaussian surface divided by the volume of the whole sphere. So this becomes the total charge Q, 2 times 10 to the minus 6 coulombs, times the ratio of the volume of the Gaussian surface divided by the volume of the sphere. And so now we can plug in what these things are equal to. So in this case, that would be E times the area of the Gaussian surface will be 4 pi r squared, r being the radius of the Gaussian surface, and of course the surface of a sphere is simply 4 pi r squared. That equals the total charge Q times the ratio of the volume of the Gaussian surface, which is 4/3 pi times the radius of the Gaussian surface cubed, which is r cubed. That's the volume of the Gaussian surface sphere, divided by 4/3 pi r cubed, r of course being the radius of the whole sphere. Notice that the 4/3 pi cancel out right here. And then we have simply the ratio of r cubed, r being the radius of the Gaussian surface cube, divided by r cubed, r big R being the radius of the whole sphere cube. And that ratio will give us the total charge inside. And of course, we still have to divide it by epsilon sub naught. And of course, here I make sure that I put epsilon sub naught there as well. Can't forget about epsilon sub naught. All right, then all we have to do is go ahead and take this and solve this for E. And so we have the electric field. E is equal to, I don't have a lot of room there, so I'm going to migrate over in this direction. So let's put a line here. And so we're going to continue here. So E is equal to the charge Q divided by epsilon sub naught times little r cubed divided by big R cubed. And then the 4 pi r squared is also going to go on the denominator. So here we go. This will be times 4 pi r squared. And of course, this r squared will cancel out 2 of those. So we'll only left with 1 r in the numerator. And so finally, we can say that the electric field is equal to Q times r divided by epsilon sub naught times 4 pi r cubed. Now, 4 pi epsilon sub naught is also equal to K, the constant we used in the Coulomb's law. So it could also be written as E is equal to K times Q times r divided by r cubed. So either way, whichever way you prefer, remember that K is simply 1 over 4 pi epsilon sub naught. And K, of course, at 9.9 times 10 to the 9th newtons meter squared per coulomb squared. All right, so now if we want to put some numbers in there, we can go ahead and do it, but since I have not a lot of room, I'll just leave it as is. So this is simply the result of the electric field strength inside a sphere that has uniform charge throughout the entire sphere. Okay, now we're going to do the second part of the problem where we try to find the electric field strength outside the sphere. Now what happens is we're going to draw a really big Gaussian surface, one that has a radius of 10 meters in this case, and so that the electric field will be right on the surface again. Since it's symmetrical, the electric field direction will always be perpendicular away from the surface. So using this equation right here, we can say that E the electric field strength anywhere along the Gaussian surface, times the total area of the surface, which will be 4 pi r squared. That's the surface area of a sphere. Remember, in this case, little r is bigger than big R. Little r is all the way out here. Big R is simply still the radius of the sphere. And that will be equal to Q inside. Now, the charge inside will be the same as the charge inside the sphere, which is simply Q divided by epsilon sub naught. Okay, then finally we can then simplify this for E. E will be equal to Q divided by 4 pi epsilon sub naught times r squared. Now, epsilon sub naught times 4 pi, 1 over that is equal to K, so this can be written as E is equal to KQ over r squared. And notice that this is the format, the general format of the electric field for a point charge with charge equal to Q, distance r away from the charge. And so we now realize that even though the charge is evenly distributed inside a solid sphere like that, if we're far enough away from the sphere so that we don't have the edge effects being very, very close to the sphere, this acts like a point charge a distance 10 meters away, and that's the exact result that you get with Gauss's law as well. So if you're inside the sphere, this will be the result. If you're outside the sphere, that will be the result, and that's how you calculate it.